In this paper, we solve the problem of reflection removal. Given an image with reflections, its goal is to generate its corresponding clean background. When users take photos through glasses, the content of the captured image comes from two parts. First, the transmitted background light behind the glass. And second, the reflected light against the glass that comes from the same side of the camera. In a mathematical function, the captured image can be formulated as the summation of a background layer and a reflection layer. However, such a problem is highly ill-posed, due to numerous solutions to this equation. To ease such a problem, the traditional approaches solve this problem by taking advantage of the motion difference between background and reflection layer in multiple frames. For this example, the background scene is projected at the blue point, and the reflected object at the orange point. When users move the camera to shoot a video sequence, the projected blue and orange points move to a new position in the 2D image. Due to the depth difference between background and reflection, the 2D motion also differs. To solve an objective function involving the motion cues, the reflection can be separated from the background layer. The traditional approaches solve this problem with a theoretical understanding of the reflection generation process, but are limited by the number of input images. With sufficient reflection and background training pairs, the recent data-driven approaches are applied to solve this problem by learning the prior knowledge of single image reflection removal. However, due to insufficient real-world reflection data, the learning-based methods are mostly trained on synthetic data, and transfer weakly to real cases. In this paper, we combine the advantages of both types of methods. We leverage a deep neural network that learns a deep reflection prior from multiple images in the training process in a more theoretical manner, and generalizes well to real cases from a single input in the evaluation stage. Similar to the traditional approaches, our problem setting takes multiple images as input, where their backgrounds are static, and only the reflections are different. For simplicity, we'll take two input images for illustration. However, this is just for the training purpose. During evaluation, we only take single reflection image and estimate the clean background. To enable multiple inputs for our learning solution, we leverage one reflection removal network, that is fed by two inputs iteratively, to generate the corresponding background and reflection images. Inherently, we assume both the predicted backgrounds are the same with each other. By randomly combining one predicted background and one reflection, we synthesize 4 reflection images. In order to leverage the displacement difference between background and reflection similar to traditional approaches, we design 3 types of losses as supervision. The most straightforward supervision is to minimize the difference between recomposed images and input samples. However, a naive solution will be achieved by setting the background layer as all zeros, and reflection as the input image. Here are the corresponding visual results. To differentiate the background and reflection, we append one supervision to avoid the background from being all zeros, by minimizing the difference between the predicted background and input. Here are the results with reconstruction loss and floor rejection loss. We further penalize all the background pixels which are bigger than the corresponding input pixels, to ensure the predictions are in normal image intensity range. As can be seen from the visual comparisons shown here, the results of our full pipeline achieve the best performance. The reflection removal network is a one-branched neural network with one input and one output. And both the background and reflection share the same output. To enable such a feature, we learn a controllable latent code, embedded within the deep neural network that is capable of switching between the background and reflection output. For each image sample, we iteratively feed the background and reflection codes to the network, to generate the background and reflection layer respectively. Such latent code is implemented as the weights and bias in the first instance normalization layer. The unique information between the background and reflection is completely embedded in this short-learn vector. To study the features we learned with this latent code, we deactivate each channel of the feature maps after the first instance normalization, by setting its values to all zeros, and compute the difference between the manipulated and untouched output images. The results of the 64 feature maps after the first instance normalization layer are shown here. The active feature maps are allocated differently from each other. We also visualize the common feature maps between background and reflection for better illustration. A similar phenomenon also transfers to other examples. Here we show some visual results. For more results and technical details, please refer to the paper and supplemental file. Due to the lack of large-scale real background and reflection image pairs, our network is trained on the synthetic reflection data. In order to test our network on the cases with the slightly misaligned background that is more common in real world, we further experiment by training our neural network on one pair of captured real images with different reflections, in an iterative manner. We also successfully remove the reflections here. Note that in this case the network overfits the single training sample, but it still demonstrates the effectiveness of our developed objective functions. Thank you for watching.